Hi, I'm Sam Hart. Today I'll be presenting on leveraging phase change for CubeSat propellant positioning. First, the motivation. Why do we want to do this? Anytime you're using a liquid propellant in space, you need some means of maintaining its position within your tank and keeping the liquid and the vapor separate. That way you can pull out a nice single-phase mixture to send to your thrusters. Now, in conventional spherical tanks with propellants like hydrazine, we've gotten very good at this. We have lots of systems that work, and we've been using them for a long time. But CubeSat cold gas propulsion systems present some very interesting problems. First is conformal tank geometries. To give an example of this, I have an image of the visor's propulsion system on the upper right there. Now, inside of that sort of off-white structure is all of the propellant tanks, the nozzles, and the fluid routing for the entire system. And it's all additively manufactured into one large block. Now, what's really great about this is we can make very efficient use of the space inside of a 6U CubeSat, which maybe doesn't fit a nice spherical propellant tank very well. But the downside is, if you take a look on the bottom left, that's the internal geometry of one of the propellant tanks in this system. As you can see, it is very much not a sphere, which means that our traditional propellant management technologies aren't going to work terribly well. Now, the next challenge we find in these systems is that they use two-phase propellants. And we do this for a couple of reasons. First, a two-phase propellant is a liquid-vapor mixture stored at saturation pressure, and that liquid is much, much denser than a gas. So we can form these systems that have a very high propellant mass and a very small volume because of the density of the propellant. That's great. It means we get more delta V in the same space, and everybody loves that. Now, the next reason we like these propellants is they self-pressurize. So because they're stored at saturation pressure, if you pull a little bit of vapor out of the tank, the remaining liquid will actually begin to boil, and it'll boil until saturation pressure is reached again. That means that we don't need any sort of pressurant gases, we don't need pumps, this is all going to pressurize itself. That's nice and makes for a much simpler system. But when that propellant boils, we're going to get small bubbles nucleating all over the walls inside of the tank. And that's going to effectively take our one large ullage bubble and redistribute it into lots of small ullage bubbles all around the tank. That's much harder to manage with a propellant management device than just one big bubble. So we have some problems. You might wonder, how are we handling this in current systems? And to demonstrate that, I have a diagram of the Marco propulsion system on the bottom right. Now, this was developed by VACO for JPL, and two of them flew to Mars. The way they work is when you want to fire a thruster, you pull gas out of that vapor tank in the middle of the image there. That vapor is then expanded through a nozzle, you get thrust. Now when you do this, the pressure in the vapor tank is going to drop, so you need some means of repressurizing it. The way VACO goes about that is they pull a two-phase liquid-vapor mixture out of their tank on the left. That liquid-vapor mixture is then routed through an inline heater that vaporizes all the liquid propellant. From here, this newly vaporized gas goes through a pressure control valve that's able to regulate the flow rate into the vapor tank. Now, if you have a nice closed-loop control system, you can then maintain a pretty constant pressure in that vapor tank, you get pretty constant thrust, and you have a working system. Now, this might seem great, but there are a couple of downsides. The first one is the amount of power it takes. I did an initial estimate of the power we would need to do a similar system for the visor's propulsion system. And it would be about 10 watts per firing nozzle. Now, we fire up to 3 nozzles at once on visors, which means that we're going to have up to 30 watts of power that we're pulling. And on a CubeSat, that is a lot of power. But the next issue, which is true of all two-tank systems, whether they have the inline vaporizer or some other mechanism of separating the liquid and vapor, and that is that they take up a lot of space. Having two tanks is always less volumetrically efficient than one tank. In addition, each tank needs its own suite of sensors, you need valves that connect them, in VACO's case they have heaters on every tank, and all of these separate components add up to a lot of mass and volume. Additionally, there's some complexity in these systems. We need some means of maintaining the right amount of vapor in the vapor tank, whether that's mechanical systems or some sort of electric control loop. All of this leads to a system that's going to be heavy, complex, big. We like to avoid all of those things, especially in university CubeSats. We really like to go for as simple of a system as we can come up with, something reliable, easy to build, and cheap. And so this puts us in search of a better propellant management system. The first technology we're going to look at is a capillary system. These have been used for a long time in space, they have a lot of heritage, and they work really well in traditional spherical tanks with conventional propellants like hydrazine. We have an example of one such system in the bottom left. So in this spherical tank, we have a sponge-style capillary PMD in the bottom. A sponge-style PMD is really just a bunch of metal panels arranged to make a series of wedges. Liquid then wicks into these wedges due to capillary pressure, and you're able to hold the liquid propellant at the bottom of the tank. So when you want to extract liquid, you can easily pull it out from a port at the bottom of the tank as shown here. Now if you design one of these systems well, it can also position the vapor ullage bubble at the top of the tank and hold it still. So you can then vent vapor from your tank anytime you need. Now this is great in those conventional spherical tanks with traditional propellants, but it doesn't work so well in our system. So if you take a look in the upper left, we have a notional conformal propellant tank. And inside of it, I've catted up just an idea of what a capillary PMD might look like in this system. And I can tell you right now, it's not going to work. It's not going to work for two reasons. First, this system is angular even without the capillary PMD in it. So liquid is going to want to wick into all the pre-existing corners and angular geometries in the tank. That means that when we put in our capillary PMD, it's trying to wick propellant to somewhere else, the capillary PMD is in essence fighting the natural behavior of the tank. And that's a problem. But a bigger problem is all those small bubbles I talked about previously. Capillary PMDs perform very poorly with small bubbles. And the reason for that is that the way bubbles are moved out by a capillary PMD are essentially that they are squeezed out by capillary pressure. For that to happen, a bubble needs to be big enough to touch both sides of your capillary wedge. So you can imagine if you have really small bubbles, you suddenly need very narrow wedges. Now, you can imagine if the bubbles get really small, your wedges start getting so narrow that if you need a bunch of wedges side by side to fill the bottom of your tank, you eventually have a capillary PMD that's just full of metal panels and it can't really hold much propellant. And so if we have a propellant tank that's not holding much propellant, that's kind of defeating the purpose of what we're trying to do here. And that's a shame, because we love these capillary systems. We really want them to work. They have a lot of flight heritage, and that makes people very comfortable. So now we need to seek out a technology that could make them work. So the next technology we're going to look at is a capillary system with a heater. Now the idea here is that basically, because the propellant is a two-phase mixture stored at saturation pressure, it's always on the edge of boiling. And that means that if we heat up part of the tank, the propellant around that hot spot is going to begin to boil. When it does that, the pressure in the tank rises, and bubbles in the colder parts of the tank will actually begin to condense because of that higher pressure. So if we run the heater long enough, you can imagine most of the vapor is going to exist in this new hot region near the heater. So now all we need to do is somehow hold that vapor bubble there so we can consistently extract it and send it to our cold gas thrusters. Now it's very easy to design a capillary system that holds one big bubble in place once it's already there. I have an example of that shown in the middle here. Now this design is just sort of notional, but it does in fact work. And we modeled it in Surface Evolver to make sure it functioned as expected. Surface Evolver is just an industry standard software for simulating the geometry of fluids in microgravity. As you can see, we have a nice big blue vapor bubble that sits nicely at the top of our tank, right over the outlet, which means we can consistently extract a vapor. And that's great, but there are some downsides to this system. First, it weighs 232 grams and it has a volume of 86 cc's. To put this in reference, in the vapor tank on the Visor's propulsion system, it only occupies about 70 cc's. So already this is bigger than the vapor tank on Visor's, so we're not necessarily going to be much smaller. That's not great. The next issue is the mass of the system, 232 grams. That's substantial on say a 6U CubeSat, where you might only be looking at maybe 6 kilograms to 9 kilograms overall mass. Now, there is a third problem that's maybe a little harder to see. But if you imagine you're boiling your propellant on this heater, right? Who's to say it's going to form one large bubble and won't instead form many small bubbles? And maybe they coalesce into one big one, and maybe they don't. Now, if they don't, that means we have sort of this bubbly, foamy stuff at the top of our tank. When we try to pull gas out, we're going to get instead that kind of gas-liquid mixture. And that defeats the whole purpose of what we're trying to do here. So we need some other technology that can force those bubbles to coalesce into one large one. So the next technology we're going to look at is magnetic positive positioning, or MPP. Now, MPP relies on the fact that all fluids experience an inherent body force when they are subjected to a gradient magnetic field strength. This is true of diamagnetic, paramagnetic, and ferromagnetic fluids. The force is very small, so on Earth we don't notice it so much, but in microgravity it can be the dominant force. Now this has been demonstrated in microgravity, so we know it works, and not only does it work to move bubbles around, but it's actually been shown to be able to coalesce bubbles as well, so it can turn our foam into one big bubble. Now I have a COMSOL simulation on the left of an MPP system in a 1U 10 by 10 by 10 centimeter cubic propellant tank. At the bottom of the tank, we have a Hallbach array composed of N52 neodymium permanent magnets. This Hallbach array's whole job is to have a very strong magnetic field above it and a very weak magnetic field below it. And it does that. Now, I've got contours here of the acceleration the liquid propellant is going to feel within the tank. So you can see very close to the magnet, we're getting an acceleration of up to 10 millimeters per second squared, and that's how fast the liquid is accelerating away from the magnets. But very quickly, as we move away, that acceleration drops off. So you can imagine that if we had a 3U tank that's much bigger, we're going to have almost no acceleration on the far end of the tank. So this isn't going to work well on its own. But if we pair it with our heater, suddenly we have a much better system. The heater pulls all the vapor up to the top of the tank, forms a new bubble, and the magnets are able to hold the bubble there. And not only can they hold it there, but they can coalesce that foam. This is great. It's already outperforming that capillary system we previously talked about. But on top of that, this is also much lighter. So now we're at 77 grams as opposed to over 200, and only about 10 cc's as opposed to about 80. So we're smaller, we're lighter, we work better, everything's looking good here. But we still wonder, could we do better? Is there something else out there? So the next technology we'll look at is a dielectrophoretic system, or a DEP system. This is somewhat analogous to MPP in the sense that we're using gradients and fields to have an effect on the positions of liquids. But instead of a magnetic field, here we use a gradient in the electric field. Now, for dielectric fluids like R236Fa, a very common CubeSat propellant, the liquid is actually attracted to areas of high electric field intensity and the gas is repelled. So if we were to string a bunch of wires through the bottom of our tank, charge some of them up to say 1 kilovolt, and ground the other ones, we could then form very strong electric fields around them, and as a result, we could get very strong accelerations. We have yet another COMSOL simulation here on the right that shows the accelerations of the liquid field towards the wires. And it's kind of the same story as last time. Close to the wires, lots of acceleration. Further away, not so much. But the joy of this is wires are light, so we can put in as many as we need to make sure there's strong accelerations everywhere we want them. So if we have a heater at the top of the tank, it can form a nice bubble at the top, and the electric field at the bottom of the tank will hold all the liquid down there and maintain its position. Now, this system has been thought of before, or at least the dielectrophoretic aspect of it has. It was actually explored fairly heavily in the 60s, but they gave up due to concerns about arcing. They were looking at using it in very large tanks, which require very high voltages, and so you get arcing potentially in your tank. But because we're so small, we're able to use much lower voltages, and as a result, arcing is no longer a concern. Now, this system is also really cool because it's adaptable, and you can adapt it in a couple ways. First, if you change the position of the wires, or if you make it so you can actively change their potentials in flight, you can generate some very interesting electric field geometries. As a result, you can force the liquid around in very interesting ways. The system's also great because it's super light. We're looking at 26 grams and only 2.4 centimeters cubed, and that includes the power processing unit. So very, very small. But there are some downsides here. The big one is that this is very hard to build. Stringing wires through your tank like this is a design nightmare. Sealing up all the ways that these wires come in and out of the tank is challenging. Also, people get a little bit touchy about running 1 kilovolt in their tank. Understandably, you can do it quite safely, especially for non-conductive propellants like most refrigerants, but people still feel a little uncertain when you first bring it up to them. The final issue is that in this geometry, it's harder to guarantee that the bubbles at the top of the tank are going to coalesce like they do in the MPP system. You can make it happen if your wires are positioned appropriately, but it is much harder to guarantee. So for that reason, this system is maybe not quite as sure of a performer as the MPP and heater system is, but nonetheless a very interesting technology worth exploring. But I've now spoken to you for about 15 minutes on these various wonderful technologies that use a phase change mechanism. But we haven't really proved that the phase change mechanism works. Nobody's done this before, and so we've got to wonder, is this all made up or is it actually going to function how we think it will? So we aim to test that. And the way we're going to test it is by carrying out tests in Earth gravity on flight-like hardware. I have a piece of flight-like hardware shown here. It's an aluminum tank with an acrylic window clamped onto the front and back to seal it. Now we're going to fill this with R236FA, an actual cold gas propellant. We're using it on the Visors mission. Various other missions have used it as well. On the outside of this tank, we have environmental heaters and chillers so we can simulate various aspects of the space environment. Inside, we have a number of thermocouples so we can see how the temperature varies throughout the tank. We also have a repositioning heater shown in the upper right there. That's the one that's actually going to boil the propellant and move the bubble around. Now, because we picked this nice heart-shaped geometry, we can start with a gas bubble in the left lobe of the heart there. When we turn on our heater, a new bubble is going to begin to form in the right lobe, and the bubble on the left should condense as the pressure rises, or so we hope. So we test this out, and in our first test, we found that after 15 minutes of testing, we'd accomplished exactly what we expected. The bubble had moved mostly to the right side of the tank, the one on the left had mostly condensed, but even after 20 minutes, still a small bubble remained on the left-hand side, and we had to cancel the test due to concerns of overpressurization. Now, this seems like a great proof of concept, but when we did our analytical approximation, where we assumed all the input power contributed directly to vaporization, we estimated that this repositioning of the bubble would happen about 200 times faster than it did in our test here. So something's going on. And to get a little more insight into what that might be, we're now going to look at the plots of temperature from the various thermocouples inside. Now T1 is the heater, or the thermocouple closest to the heater, and T's 2 through 5 are progressively further away. So you can see when we start the test, T1's temperature immediately spikes up, and then when T1, that thermocouple, enters the vapor bubble, we suddenly see a very significant spike up to 70 to 80 degrees Celsius. Now, if you look at T's 2 through 5, we can see the rest of the tank rises about 3 degrees Celsius over the course of the test. And so we can learn a couple of things from this plot. First, the whole tank is heating up, so not all of our heat is contributing to vaporization. Instead, we're actually heating up the bulk fluid as well as the tank itself. The next thing we note is that vapor bubble is hot, and it's surrounded by a highly thermally conductive aluminum tank, which means we're probably losing a lot of heat into the tank walls. It's not only conducting around the entire tank, which is part of why the whole system's heating up, but also we're losing a lot of heat to the environment. So we then thought, all right, if the thermal conductivity of the tank is the reason it's performing so poorly, then a nylon tank should perform better, right? It's not non-thermally conductive, but much less thermally conductive than aluminum, so we expect better performance. So here's a demonstration of a nylon CF10 tank. So this is nylon with a little bit of carbon fiber in it, and it makes it into a nice 3D printable material that's very strong. So we have our nylon CF10 tank. Using the same power as in the last test with a comparably sized vapor bubble and about the same geometry, we're now able to move the bubble over in just 65 seconds instead of over 20 minutes. So that's great. It's over an order of magnitude improvement. We also found if you crank it up to say 17.2 watts, so you really ramp up the power, we can move the bubble in under 30 seconds, which is nice. But we then went ahead and made this algorithm. What it does is it tracks the liquid vapor interface, which means you can effectively track the size of the bubble on either side of the tank. So I have plots here of the rate of shrinkage of that left side bubble. So how fast the left side bubble is condensing. Now we can see in the 3.3 watt test in particular, there's sort of an interesting change in slope right around 30 seconds into the test. What's happening there is the heater stops being fully submerged. And as the test goes on, less and less of the heater is submerged in the liquid, and more of it's just sitting in the vapor bubble. And as one would expect, that means there's a lower rate of heat transfer and the vaporization rate really drops off. We can learn some interesting things from this. Primarily, we want to keep that heater wetted as long as possible. And there's a couple ways you can do that. For one, you could put the heater in sort of a capillary geometry, perhaps in a corner of the tank, or you could design a capillary propellant management device to hold liquid up against that heater as long as you can. Next, you can actually use an MPP system to pull bubbles off the heater. And this has been demonstrated primarily for electrolysis in the past. But by pulling bubbles off the heater, you're effectively keeping it in contact with liquid more often and increasing your heat transfer rate. So using these two phenomena together, we can keep the heater wetted and vaporizing as quickly as possible. Now, in conclusion, phase change PMDs could offer a compact, simple, and low-mass solution to CubeSat cold gas propellant management. But before they're ready for flight, there's still a lot of work that remains to fully characterize this system. And we're continuing to do that work here at the Georgia Tech SSDL. With that, I'd like to acknowledge the National Science Foundation for paying for my school. Really appreciate it. And here is our contact information. Should you have any questions about the presentation, feel free to reach out.